We were discussing joint spectrum of K commuting self-adjoint operators. So we define joint spectrum. So T1 up to Tk, G of H, commuting, they are mutually commuting, and self-adjoint operators. Then we define this Tk. Since these are self-adjoint, this will be contained in Rk equal to all those lambda 1 up to lambda 2. Such that they are all approximate eigenvalue with joint approximate eigenvector. Ti minus lambda I xi such that there exists here z in H such that is less than you can define it for epsilon or you can define it as a sequence such that T minus lambda Ti minus lambda I n goes to 0. Okay. There exists joint approximate eigenvectors as this lambda 1 up to lambda k as lambda I eigenvalue of lambda Ti. Lambda I is an approximate, it's actually eigenvalue. It's actually in the spectrum, not eigenvalue, approximate eigenvalue. And it admits a joint approximate eigenvector. Then we proved that this is K is compact. And we want to prove it's non-empty. So we were towards proving this. So if pi I, we used pi I, pi is used for that particular, we use pi for the representation. For the time being, I use pi for this projection. Okay. Or you can use Fi, for example. Okay, let's use Fi. Fi is because it can be, it can be later used as this is also a polynomial in one variable or something. Fi is just T1 up to Tk going to Ti, right? Okay, so Fi is a function from sigma to Tk, where F of T1, Fi of T1 up to Tk is Ti. Okay? Then Fi of this sigma T1 up to Tk is just sigma of T. So this is what we want to do. We are proving towards this. There was some confusion about the eigenvalue being when eigenvalue is 0. So we use induction. So for k equal to 1, it's true, proposition is true. And assume proposition for k. We want to prove it for k plus 1. Okay. So let T1 up to Tk plus 1 will be of its self-adjoint. Okay. Then we want to, then for lambda in sigma of Tk plus 1, we need to exhibit, we want lambda 1 up to lambda k in the sigma of T1 to Tk, such that this lambda 1 to lambda k plus 1 is in sigma of T1 up to Tk plus 1. Right? This is what we want. Okay. We want to prove that the projection of this sigma, when you project it to the k plus 1 coordinate, is sigma of k plus 1, sigma of Tk plus 1. To prove that if there is a lambda, then we should exhibit something in this set, so that when it, when you do this, you get this. Okay. It just follows. We don't even need this. We have to prove this statement. Sorry, this is what we need to prove, but that will follow from this, of course. Okay. So for this, we choose for n, we choose, so let Pn equal to 1 of this lambda minus 1 by n, lambda plus 1 by n of this Tk plus 1. And let Tni equal to, you take this Pn. So this Pn commutes with Tk plus 1. They are spectral projections corresponding to Tk plus 1 for this interval, corresponding to this interval. They, of course, commute with Tk plus 1. And by an earlier proposition, we proved using Helmholtz criterion, it commutes with all of those T1 up to Tk. Because T1 up to Tk commutes with Tk plus 1. So it will commute with all the spectral projections also. We proved that using Helmholtz that criterion. So because of that, this is just the restriction of Ti. Okay. Just consider, I mean, well, you can, I mean, I don't want to take again Pn. This is just that Tni equal to Ti restricted to this space, Pn. Okay. This is just, you consider this an operator in Pn. Okay. Okay. Then sigma of Tn1 to Tnk. Okay. The claim is this is contained in sigma of T1 to T2. This just says that there is a giant eigenvector in this space, in this, I mean, this just means that there is a, I mean, it's clear, I think, we discussed last time. So in this range of this Pn, in this range, you have a xi n, I mean, and the n may differ, I mean, a given epsilon, we have to produce a xi in this, such that it satisfies this equation, right? Ti minus that, I mean, if we have a something, mu1 up to mu k, then Ti minus mu I, that xi is less than epsilon. You have Tin. But then if you have Ti, then that is Ti acting on xi is exactly Tin. So it will satisfy for the Ti also. Okay. So this is okay. We are just taking the restriction. So this is true. Okay. But then when we get a vector in range of Pn, we take it as a vector in the H. I mean, xi direct some 0 or something. The orthogonal combination. I mean, there is some subtlety which is okay, I think. Okay. Otherwise, you have to introduce. Okay. So this is okay. Okay. So, but then we assume the proposition for k and k equal to k. So this is non-empty. Okay. Non-empty for all. Right. I mean, that's what this says. Proposition says this is equal to this means this is non-empty. Okay, this set is non-empty. So because this set is not, I mean, when the number of tuple is k, this is non-empty. We are assuming the proposition. This is non-empty. So this is non-empty for all n. Okay. This implies intersection of n equal to 1 to infinity. Is not equal to empty because they are all compact. Okay. You take compact set, decreasing sequence of compact set. Okay. Then the intersection is non-empty. You can take a sequence xn in this set and that will have a convergence subsequence and that limit will be inside that. So now choose lambda 1 to lambda k in this intersection. Okay. In this. Then that is also in sigma of Tn1 up to Tnk. Of course, it is in the intersection, so it is also here. So there exists, you take the nth approximate eigenvector. I mean, sorry, 1 by nth approximate eigenvector. I mean, see, for each n, I take the 1 by nth approximate eigenvector for this tuple. Okay? So choose Xn in this range of that. Range of that is m, I mean, what we call as m of tk plus 1, lambda minus 1 by n, lambda plus 1 by n. Which is the range of Pn, of course. Range of Pn. What's that? Pni, which is same as, I mean, because once it acts on the Xn, it is same as Ti minus lambda I, this Xn less than 1 by n. I mean, we take this projection and any element, so, and then we restrict that operator to that projection. This projection corresponds to Tk plus 1. This has nothing to do with T1 up to Tn, Tk. Okay? Then you can, because it is in this set, you can choose something like this, right? Okay, this is for all n. And since this works for Tan, it works for Ta also. Okay. Now this Xn gives an approximate eigenvector, joint approximate eigenvector, 1 by n joint approximate eigenvector for all these Tis. Okay. On the other hand, for this, it is anyway true. What is that? On the other hand, this Xn is in this set. Okay. This implies that T times 1, that lambda minus 1 by n, lambda plus 1 by n, okay, is less than or equal to, I mean, this is less than or equal to 1 by n, greater than or equal to minus 1 by n, right? So the norm of this times, so this implies the same thing holds for the, you can replace it with the operator, right? And T less than or equal to 1 by n. You can have the same inequality replaced by operator. This is satisfied by the function. Okay? So you can replace it with the operators. This will imply that norm of T minus lambda is less than 1 by n. Okay, I mean, we have already seen this. If some operator, some self-adjoint operator is between some k and minus k, or any AB, then the spectrum will be contained in the AB and the norm will be, okay. So you can, so because of the norm is less than or equal to k. So this implies norm of T minus lambda is less than or equal to 1 by n. So which implies T minus lambda of that Xi, I mean, norm of this operator, norm of T minus, not norm of T minus lambda. It is true for norm of this operator. Sorry, it is only true for T multiplied with this. So if Xi comes from this space, okay, then this is true. Norm of Xin is, I mean, this is k plus 1, no? Sorry, this is k plus 1. This k plus 1 is less than 1 by n, which is automatically true because Xin comes from that space. I mean, if Xin comes, I mean, if you have a Xi in this space, the range of this, I mean, I just read the operator, range of this space, lambda minus 1 by n, lambda plus 1 by n, then it is automatically an approximate 1 by n approximate eigenvector for that with eigenvalue lambda. Okay. Because it satisfies this equation and it satisfies further. So this gives this implies lambda 1 up to lambda k, lambda is in this sigma of C1 up to Tk plus 1. So proposition is true. This is what we want to prove. If this is clear, I will go to the next. We will start discussing the next proposition where there is a problem in the book. And so next we want to define, we have defined, what did we do for self-adjoint operator? We first defined polynomial functional calculus, just to substitute the t in the polynomial. Then we extended it to the continuous functional calculus. Okay, because it satisfies, because using the spectral mapping theorem. You had the spectral mapping theorem. Using that, we proved that the norm of this operator the same as norm of P. Of course, P should be restricted to the spectrum. Okay, we use this, and then using Stone-Weierstrass theorem, we extended it to the continuous function. Okay, that's what we did. We want to do the same thing, but then the proof given here is not proof given in Sundar's book is not quite correct. You overlook the fact about the normal operator. So first, I want to discuss something about the some proposition about normal operator. So this is the proposition. We proved part of it already. So P is normal. T is a normal operator. No, I want to say the following are equal. The following are equal. One, P is normal. We already proved this. Px equal to P star x. T xi. X I'm using for something else. For all xi in H. Okay. This is just, we already know that. T star equal to P star T. That is what normal means. This is the normal equal to this, which is equivalent to this xi. This inner product xi equal to T star T xi, and which is just norm Tx square equal to norm Tx. So this is direct. And this is equivalent to that. So some operator is uniquely determined by this quadratic form we prove using the polarization identity. So this is equivalent to this. The third condition is if T equal to T1 plus IT2, I'm sure you all know, maybe I mentioned it. Any operator T can be written as linear combination of T1 plus IT2, where T1, T2 are self-adjoint operators. Okay, where that's right, where T1 equal to T plus T star by 2 and T2 equal to T minus T star by 2i. These are, of course, self-adjoint operators. And so T1, T2 self-adjoint. Okay. So if T1 equal to T2, then norm of Tx square equal to norm of T1 x square T1 z square equal to T1 z square plus T2 z square. Okay. So fourth one. This is equivalent to T1, T2 equal to T2, T1, T1 and T2, T2. So a normal operator is an operator where its real part and imaginary part commutes. That's what this is. And proof. So one is equivalent to 2, we have already seen. 2 is equivalent to 3. We have 2 says that Tx square equal to T star x square. Okay. And this is equal to T1 plus T1, I don't know why I get this x here. T1 xi plus I T2 xi square equal to T1 xi. T star is just, you get a minus here, right? T2 xi. And this is equal to T1 xi square plus T2 xi square plus 2 real part of T1 xi I T2 xi. Okay. Equal to the same thing, T1 xi square plus T2 xi square plus 2 real part of T1 xi minus I T2 xi. Except we have a minus here. These two are equal. That's what this says. So these two has to be equal. Okay. And this implies of course, you can take the I outside. So real part of, so these two should be 0. This is just a minus of this. So these two terms should be 0. These two terms are 0 means this is real part of that is 0 means it should be purely imaginary. It should be purely imaginary is equivalent to saying this should be real, right? I times something is purely imaginary means that should be real. So this implies real part of, we are proving what? We are proving 2 implies, no. Let me only. This implies this is equivalent to this implies I mean, this two should be 0, so we get that statement. That is the third statement. Okay. Real part of whatever we have is 0, so this should be equal to this. That is the statement. Okay? The third statement is this should be equal to this. So the whatever we get the cross term, that should be 0. So that's all. Now 3 implies 4. 3 implies 4 says that norm of this is equal to this. That just means real part of this T1x. I mean, sorry, T1x, T2x, T1z, T2z is just real. That's what it means, right? This is equal to this means this term has to be 0. And this term has to be 0 means this should be purely imaginary. Here you can take the I out, as minus I or something. That just means whatever the inner product we have without that I should be real, purely real. Okay? That's purely real. That's what I have written. This just means, but then this is for all z. This just means that T1, T2 is self-adjoint. That is T1, T2 self-adjoint means T1 and T2 are self-adjoint. That just means T1, T2 equal to T2, T. And these are all equivalent statement, of course. I mean, something T1, T2 self-adjoint means this is real, this is equal to this, that is equal to this. Okay? Okay, so this is fairly clear. So now if we have a normal operator, T is a normal operator, and lambda equal to alpha plus I beta, where alpha beta are real, okay, is in the spectrum sigma of T. This is equivalent to saying alpha beta is in sigma of T1, T2. Is a statement. And that should be clear from this. So proof. So I mean, if you have a lambda in sigma T, is equivalent to saying there exists here xi n in H such that T minus lambda n goes to 0. But then T is normal, T minus lambda is also normal. So we just says that T1 minus alpha. I mean, this is the real part. If you want, you can take it again. Okay. Plus I times T minus alpha. I mean, this is the decomposition of T minus lambda. T2 minus beta. Okay. This of this n goes to 0. Okay. But then because it's normal, this is equal to T1 minus alpha whole square. This goes to go to 0. I mean, if you want, you can take square. And this is equal to T2 minus alpha n square. 0, which is equivalent to saying alpha beta. This is just, I mean, this n is a joint approximate eigenvector, 1 by n eigenvector. Okay. And this is equivalent statement, of course. Now we want to discuss the, I mean, I'm not proving it, I'm just discussing it because I haven't got a proof yet. So I will, I mean, there is one certain point we have to prove. I will leave it as a, not an exercise. I will give it as a problem. If you can solve it by Friday, so next, I will have the next class on Thursday, not tomorrow. Okay. And by Thursday, if you solve it, then I will give you some good. Thursday, 6:30. It's okay. Then we will have it Wednesday. Okay, Wednesday, Friday. Friday we will have. Okay. I mean, we will not have much to discuss. We'll have a short class. Okay? Whatever is left, we will just discuss. Okay. You have a P in, this is polynomials. Okay. Polynomial in K variables. Okay, polynomials. Complex coefficient, complex polynomial. I mean, the variables are independent variables are real variables, T1 up to Tk. Okay. But the coefficients are complex. Okay, that's what I, complex polynomials. Okay. And if T1 up to Tk are self-adjoint, then of course P of T1 up to Tk we can define. Okay. And this is a, and T1 self-adjoint and commute. We have commuting self-adjoint operators. Then we take this polynomial and insert this T1 up to Tk in that polynomial. And since they are commuting, of course, how you write the product doesn't matter, like similarly in the, as in the polynomial. Okay. And this will be a normal operator. Only the coefficients will take a bar and they will commute with each other, of course. So this is a normal. I mean, if you take the star of this, only the coefficients will become the complex conjugate and they will commute with P. Okay? So this is clearly a normal operator. Then the first statement is sigma, the spectrum of P of P1 to Pk is nothing but P of this sigma of P1. Polynomial spectral mapping theorem. Okay. This is the, I mean, for n variable, multi-variable spectral mapping theorem. Okay. Then the next statement follows easily, of course. That is norm of this P of T equal to this P as a function restricted to that sigma. Sigma is whatever I have written there, the infinity now. Continuous, uniform now. So the second statement follows easily. So we will, I mean, I will ask, I mean, if you can solve it by Friday, then of course, I'll give you marks. I will also try, of course. So if we can't do it, the statement is anyway true. I will prove the Gelfand theory, which I said I will not do. I mean, because we want to avoid all these things. Gelfand-Neymark theorem, yeah. So yeah, Gelfand-Neymark theory. Can we? For what? Which one? Well, we haven't done it in the class, so it's better you don't use it. Okay, I mean, so I mean, it's a general Banach algebra. That's what we did. So yeah, without using that, it's better to do it without that. Okay, so and if I mean, anyway, the spectral mapping theorem, although this is just a better way of doing it. That's all. Okay, without avoiding that. Huh? Spectral, which the polynomial spectral theorem? No, that holds in Banach algebra. No, that is not true for Banach algebra. That is one. I mean, even for analytic function, that's not true. Only one way inclusion we proved. Yeah, we proved only one inclusion. That's what we did. For polynomials, it is true. Yeah. So yeah. So proof. I mean, it's not proof. That's it. Indeed, if we can solve it now, it will be better. It's also okay. Okay, that's it. See, the point is, here we have, I mean, it is not true that alpha, I mean, if alpha, it says that lambda is an eigen, lambda is in the spectrum of that, that is equivalent to saying alpha, beta. If lambda is in the spectrum, both alpha and beta are, of course, alpha is in sigma of T1, beta is in sigma of T2. Okay, but not the other way is not true. Okay? Because they may have different eigenvector, approximate eigenvectors. Okay, so other way is not true. But somehow here in the book it's used that the lambda is equivalent to this alpha is in sigma of T1, beta is in sigma of T2, and he reduces to the case that we can assume, I mean, this P can be written as that Q equal to P plus P bar by 2, and R is equal to Q P minus Q P minus P bar by 2i. Okay, this is just a real and imaginary part of the polynomial. Okay, so when you take Q of the T1 up to Tk, R of T1 up to Tk, there will be they are self-adjoint operators. So says that it is enough to prove this for these two operators, these two polynomials. Okay, so first that is not true. We have to, I mean, first for then there is another complication is what I see. The complication is you have, so if you prove that Q of see one way will be true. This way will be easy. Okay? I mean, you will see that this way will be easy. You have to prove this way. So to prove this is included here, okay, you have to take no, which way is clear? Yeah, this way is clear, of course. So we have to prove this way. Okay. Okay. Now, so yeah, if you have a lambda here, lambda which is in the spectrum of this, then you have to produce lambda 1 up to lambda k such that P of that lambda 1 up to lambda k is equal to lambda. That's what you have to prove. Okay. Now for Q, you will get a lambda 1 up to lambda k with some eigenvector, some vector. Okay. And R, you will get another mu 1 up to mu k. But you have to get the same lambda 1 up to lambda k, right? Am I right? You have to get the same lambda 1 up to lambda k. That's what the statement says, right? But it is not clear how to get that. That is a problem. I will write down. Okay. So first we will prove one way. So it is not enough to prove for one Q or one R. For QR, you have to get a jointly lambda 1 up to lambda n, and you have to get a jointly eigenvector also. That doesn't, by considering only one of them, see, if you prove that to prove one, first we prove this. This is clear. Sigma of P1 up to Pk is contained in sigma of P of that P of P1 up to Tk. Okay. That is because if you have a lambda 1 up to lambda k here, that just means there exists a Zn in H such that Ti minus lambda I Zn goes to 0. Okay. Now, if you take P of T1 up to Tn, Tk, minus P of, this is scalar, P of lambda 1 up to lambda k, okay, you can take P itself, doesn't matter. You need not consider Q and other things. Okay. This Xi, okay. I mean, I'm not going to read the whole proof because unnecessarily messy here. You assume the polynomial. This is equal to, this is less than or equal to, of course, you use triangle inequality. This is less than or equal to sum of terms that you have a k, and you have a, you have a polynomial, so you will have some, T1 power k1 kind of, this is like a Ti1 power I1 to T, I1 power R1 and up to T Ik IL, let's say IL power RL. Okay. This is how it will look like, right? Some constant times, this is how the terms will look like. Okay. So there you will get, so and you can put the norm here. by triangle inequality. And here you will get the lambda I1 power R1 up to lambda IL power RL times xi, whatever this xi, okay, maybe xi n, or you can have the xi n, you have a xi n. Okay. Now this you can, sorry. So here you will get Tx. I mean, you have to substitute the TA, So you use the TX here. Okay. Now this you can take, you can write it as n terms. Keep this Ti minus lambda I and then up to the rest of the product and keep, how to write it as n terms like this. Okay. And you have to, these are all anyway finite sum. You have to show that each term goes to 0. And each of the terms, you will have some, these are all bounded operators and finitely many of them, product, and you will get a finite constant. Okay. And finally, you will get a Ti power R1 power lambda I power R1, which you can write it as T minus lambda into some numbers, which is again some constant, which all depend on, all these constants are finitely many. Okay. There is a little bit messy. I don't want to do that. So I leave it as an exercise. So this will go to 0 as n goes to infinity. Because the sum is finite, everything is finite, right? It's anyway exercise, you do it, okay? But it's clear. You will have Ti power R1. You have terms like this. This is some constant times terms like this. And here you take Ti power R1, you keep the other, all the other things. And those things again, you keep it and only keep the lambda R1 power I1, I1 power R1. Okay. Then the next term, then you take the minus of this, then plus of that, then go on, remove one term by one of the TAs, one TA in the next one. And you just keep on removing it, and finally we'll get only one term, some constant times one term, and again this is T power R. This is also true. No, T power n minus lambda is equal to T minus lambda into something. Okay. So use all that, and you can prove that this goes to 0. So one way is okay, just a calculation. Okay. So now to prove the other way. Contained in. So we have to produce if alpha and beta are in sigma of I have sigma of E of Q of T1 up to Tk and R of T1 to Tk. Then we have to get, right? This is what we should get, lambda 1 up to lambda n, lambda k in sigma of T1 up to Tk, such that Q of lambda 1 up to lambda k equal to alpha, R of lambda 1 up to lambda k equal to beta. That is what we have to prove. So the problem is getting a same lambda for both of them. I'm not able to get it. By imitating the proof he has. I was just trying 1 hour back. I didn't try it before. So see, if you have a alpha here, alpha is in sigma of Q of T1 up to Tk. If you have alpha something, then by the earlier proposition, you get a lambda 1 up to lambda k in sigma of that T1 up to Tk, lambda k, and you can insert the alpha also, okay, such that this is in this is that Q of that. By the earlier theorem, Q is a self-adjoint operator, some self-adjoint operator. You can attach it. So if you have any alpha, you get a lambda 1 to lambda k, such that this tuple is here. That is what the previous proposition says. Similarly, for beta, you get another mu1 up to mu k, beta is in that. So So if it is in this, then by the same calculation, this just means that Ti minus lambda times some xi goes to 0, right? That will by the same calculation, Q of T1 up to that minus Q of this lambda 1 up to lambda k times xi will go to 0 by the same calculation. So this will imply that alpha has to be Q of lambda 1 up to lambda k. You understand? Is it clear? I'm just saying lambda 1 up to lambda k, alpha is here. That just means there exists a xi n such that Pi minus lambda I xi n goes to 0. And also, and that Q of that whatever minus Q of that lambda 1 up to lambda k. Okay. This xi n also goes to 0. Okay. But this T1 up to T1 Ti minus lambda I xi n goes to 0 will imply that Q of T1 up to Tk, Q of lambda 1 up to lambda k xi n will also go to 0 by this calculation. But if you have one for a single eigenvector, approximate eigenvector, if you have two different eigenvalues, they have to be same. That you can see it easily. See, if for an operator, if T minus lambda xi n goes to 0 and T minus mu xi n goes to 0, then lambda equal to mu, right? Because lambda minus mu xi n equal to, of course, this T minus lambda xi n, T minus mu xi n, right? This will go to 0, right? By triangle inequality. But then this is just xi n as norm 1, right? I mean, we didn't mention, but we have been assuming. So this implies lambda should be equal to mu. Okay. So here it says that if you have an alpha, you get lambda 1 up to lambda k alpha, which is here, which is in this set. That means T minus T, I mean, Ti minus lambda I xi n goes to 0. And also Q of T1 up to the Tk minus Q of lambda 1 up to lambda k, this goes to 0. This implies that Q of that, I mean, from this calculation, which I haven't done completely, but I've asked you to do. From this calculation, Q of T1 up to Tk minus Q of lambda 1 up to lambda k will also, that also will go to 0. That should imply that Q of lambda 1 up to lambda, I mean, this alpha should be equal to Q of lambda 1 up to lambda k. Is it okay or shall I repeat? But anyway, I ask you to do it, okay? You do it. So from this calculation, this implies that Q of lambda 1 up to lambda k is equal to alpha. But I don't see how to get the same lambda 1 up to lambda k for the other one. You will only get R of mu 1 up to, you will get a sum mu k equal to beta. But somehow you have to get the same lambda 1 by some argument. Then only it will work. But we have one more condition which we haven't used. The condition is we assume that alpha beta is in this sigma of qt1 rt this. Okay. So there exists another, but that will be another vector. There exists another eta n. We have another condition. Eta n, this is n. Okay. Such that q of t1 up to tk minus alpha eta n, this goes to 0. And similarly, R of T1 up to Tk minus beta of this eta n goes to 0. I'm not sure how this is useful to get that. This is also true. Okay. There is another idea, but for that we have to use the functional calculus of normal operator, which we haven't proved yet. I mean, all these things we are doing to prove that. Okay. Using that, we can get this. Okay. I mean, this is actually true once the functional calculus is true, which we haven't, I mean, which we can, if we prove it indirectly, then we can get this. Okay. Even for k equal to 2, we are not able to prove. I mean, for that also we need this. So I'm not able to prove. You try this. I will also try. I will talk with Sundar also. when I get to see him. So this is the problem. Okay. So we will discuss this again on Friday. If we cannot do it, then I will do the Gelfand theory, which will take 1 or 2 class. Maybe this is the last week, no, before the midterm. Next week is the exam. Yeah. So we will discuss Gelfand theory after that. We assume this for the time being, which is anyway true, because using this only, we are going to prove the functional calculus for normal operator, which I will prove using Gelfand theorem if we cannot do it. Okay. So for the time being, we'll assume this. Okay. So then the second one is easy, direct. The second one says that, what is the second one? Second statement is norm of P of t is equal to P restricted to, the infinity norm of this polynomial restricted to sigma. And that is the same proof. Same proof for norm of P of T1 up to Tk, which is equal to, by this, whatever we have, sigma of this is equal to sigma of this is equal to the spectral radius of this, right? The spectral, because it's a normal operator, T1 up to Tk, yeah, spectral radius of this. And that is equal to mod of supremum of mod of Z, okay, where Z is in the spectrum of this, P of T1 up to Tk. Okay. But this is equal to supremum of mod of P of Z, P of T1 up to Tk, okay, where T1 up to Tk is in that sigma of T1 up to Tk. Okay. And this is exactly the supremum norm, P restricted to that sigma of infinity norm. Okay. This is the same thing which we have done earlier for the self-example. It's the same thing. Okay. See, there is no star structure. The polynomial spectral theorem, we don't prove that we prove spectral mapping theorem for polynomials, which is for real polynomials. Complex valued polynomial with complex coefficient, but the variables are, there is no there is no bar in that. So that is the only complication. Okay. Otherwise, we can apply the same thing to, for the second statement, we need the Stone-Weierstrass theorem. For that, we have to, the Stone-Weierstrass theorem, the algebra should be closed under complex conjugation. No, that is not guaranteed by the polynomial spectral mapping theorem. So if we assume the second statement, then this follows immediately. So theorem, maybe a theorem. This is multivariable spectral mapping theorem. So there exists a unique isometric star isomorphism call it phi from C of sigma of T1 up to Tk. Of course, we assume T1 up to Tk, self-adjoint, commuting, all that. Okay. 2, that C-star algebra, I add 1 because we have improved that it's unital. I need not add because we assume that it's a unital algebra generated by that. So we take polynomials with constant terms and then we take polynomials in T1 up to Tk with the constant term and take the closure. Okay. T1 up to Tk. We take the C-star algebra generated by this. So there is a unique isometric isomorphism from here to here, such that phi of this function, fi is a projection, is equal to Tn. Okay. So this is one statement. Second statement is there exists a measure same statement, imputing mu on the sigma of P1 up to Pk and a pi tilde, unique pi tilde from L infinity of sigma mu, okay, to this into B of h, such that again pi tilde restricted to that C of that sigma is pi. And you know the convergence statement. Should I say it again? The same statement. Fn bounded, Fn converges to F in mu implies, which is equivalent to actually pi of pi tilde of Fn converges to pi tilde of F strongly. Okay. There exists a measure and a pi. This is again isometric star isomorphism. Okay. Because we have proved this pi extension pi and pi tilde for a general C of x, okay, for a general C of x. So first you have this representation. Now this is clear. The proof is clear. Okay. You have this pi of fi. You define pi of fi equal to pi. This implies by algebraic thing pi of p of t1 up to p is the polynomial. P of t1 up to tk is equal to, of course, p of t1 up to tk. You take this polynomial. This preserves the norm, and by Stone-Weierstrass theorem, they are dense. This preserves the norm by the previous statement. By Stone-Weierstrass theorem, that extends to a star isomorphism. I mean, sorry, Stone-Weierstrass theorem, they are dense. Since it preserves the norm on a dense subspace, it will extend to a, and it extends because, I mean, it extends is again an algebraic isomorphism because star is continuous in norm and this multiplication is continuous because of all that. I mean, we have already used all that. Okay? So because of that, this is, yeah.
There exists unit measure or
the measure will be again absolutely continuous. Yeah, the measure, I mean, you can use the same thing.
okay.
The same proof will work. Okay. Yeah. There can be two measures because it is only the L infinity is uniquely determined. So if you have mu and nu, they will be mutually absolutely continuous. So the same proof will work. You take any projection, you will approximate by this. I mean, continuous function. It is the same thing. Okay. So I don't have to write the next statement. It's all clear. Okay. So this is the spectral theorem. Now, if you take k equal to 2, that is the spectral theorem for a normal operator. Okay. So this is the theorem. We can slightly change it, spectral theorem for normal operator. So T in B of H is normal. Then there exists, you can write it in terms of sigma T1, T2 if you want, or directly you can write it. There exists a unique star isomorphism pi from C of sigma of T to C star algebra generated by this T, okay, which you call it as F going to F of T. Okay. Here also you use it the same notation, F going to F of T1 up to Tn or something, T1 up to Tk or something. Okay. There exists a pi from C of sigma T to C star T, F going to F of T, such that pi of this function f naught equal to f naught, if f naught equal to t, where f naught of z equal to z. Here there is a slight change. I mean, instead of I mean, you can prove, you can identify sigma t with sigma of T1, T2, T1 and T equal to T1 plus IT2. I mean, instead of this, you can consider two functions. F1 of Z is equal to real part of Z, F2 of Z is equal to imaginary part of Z. Then by the previous theorem, you get one single, I mean, if F1 of F0 of Z equal to Z means, then the two functions also, this means that pi of F0 equal to T. That means if you have F1, see if you have the function F1 of Z equal to real part of Z, okay, and F2 of Z equal to imaginary part of Z. Okay. Then F0, pi of F0 equal to T will imply that pi of this F1 is T1 and pi of F2 equal to T2. Right? And then the previous proposition you can use. Right? Previous proposition says that there exists a unique homomorphism such that pi of Fi is the coordinate projection. The coordinate projection here are the real and imaginary part. Okay. I don't have to write it, no, write the details. It's clear to you. Okay. And then they'll, of course, then again the L infinity extension. There exists a measure on this. I mean, there is no involvement of real and imaginary part. The statement we can directly make for the sigma t itself. That's what we are writing it. And it follows from that. Okay. Now, then there exists a measure mu on the sigma t such that again the same statement. Whatever we have written for the self-adjoint operator, the same statement is true. Okay, that's all. Okay. So now I want to define, since I have 15 minutes, I will state the actual spectral theorem. What is the spectral theorem? This is the spectral theorem actually. So we call them projection valued mapping, so the definition. And we can say for C, so let P be a mapping from Borel sigma algebra of C to P of B of H, P of H mapping. This is just projections in H. Okay. You take the collection of projection, which I call it as P of H. Okay. So P is a mapping from the Borel sigma algebra to P of H, okay, such that which is strongly additive. That's all, strongly sigma additive, such that P of empty set has to be zero projection. The P of the one, I mean P of the whole set, it should be equal to the one, and the P of summation P En equal to summation of P of En, where this is strongly, okay, summation P of union of En, disjoint union of En. Empty. Okay. We have a disjoint union. P of this is equal to summation N equal to 1 to infinity P of En. This is strong convergence. Okay. This infinite sum is in the sense of strong convergence. That's all. This is called a spectral measure. This is just a measure which takes the values and projections instead of real line or something. That's all. Okay. So this is phi. This is phi. So how will you define this? We have already defined it, the spectral projections. So proposition, there exists a unique spectral measure. So T is normal, T in B of H normal. Okay. Then there exists a unique spectral measure corresponding to this T, P from Borel sigma algebra C to B of H, C of H. Okay. such that the following statements are true. One, I mean, these are all immediate consequence. For any xi in H, okay, this map E going to can define mu of E equal to inner product of P of E xi xi. Is a positive measure, is a probability measure. Measure on BC. First statement. Yeah. Second, for two vectors, mu of E. So here I put a xi here. Okay. Here I put xi eta of E equal to P of E xi eta. So, I mean, when you fix a xi, this gives a positive measure. Okay, positive probability measure. When you fix a xi and eta, then this so no, only when norms are equal to 1, this is a probability measure. So this is not probability, I'm sorry. I mean, it's not probability measure. With P of with mu xi of whole set C is norm xi square. And this is equal to 1, it's a probability measure. Okay. When you have xi and eta, E, this is a complex measure. With there is something called norm of a measure, total variation measure, which is you have to take all partition, take the supremum over the sum of this. So if you have a sum mod mu, maybe mod mu, mod mu is a measure. Mod mu of any E is equal to supremum of you take any partition, okay, En equal to E, mod of, this is mod of mu of En. I mean, this is a complex number, you take the mod of that, and then you take the supremum over this. This is mod U is a measure of the, I mean, mod of the measure, supposed to be mod of the measure. Set of all complex measures is a vector space, right? You can multiply, you can add two measures, right? Complex measure multiply, which is a vector space. This will give a norm on that space of complex measures. Rees representation theorem says that that is just the dual of the continuous function, right? That's what it says. Okay. So mod of mu xi is equal to this xi eta. Then the third statement is integral f of lambda, or you can just put, if you insert just lambda, you will get t. Okay, f of lambda dp of lambda, okay, integrated over c. I mean, the integration will be over sigma t. We are just writing c for general reason. This is equal to f of t. Okay. This actually what it means is, I mean, this is integration on a Banach space, right? Integral, the measure, I mean, this is like a, these are all scalars. These are all operators. Okay. I mean, when you write it like summation lambda I p of ei, this will become an operator. Okay. So you are having a sum, and the integral is like a limit, right? Integral is a limit of finite sums. Okay. Some, if you for simple function, you can define it like that. For summation, if you integrate summation 1 ei, if you take a simple function, to take the integral, that is going to be lambda I p of ei, right? This is how you will define the integration. Okay. And then if you take this is just suppose some simple function converts to some f, then this integral is just the limit of that. And in which topology you take the limit, that is the question. You take the weak topology. I haven't said what is a weak topology. Weak topology is not the Banach space weak topology you might have discussed. This is called operator weak topology. There is, so whatever I'm going to write, this is the meaning of this by this. Okay, this is just the meaning. You can take it directly. This just means that this f of integral, this is an operator, right? this just says that, I mean, whatever the convergence I am saying, that convergence, the operator, you have a T lambda converges to T in operator weak topology. This is not the weak topology. Weak topology usually is the dual, I mean, you take the topology given by the dual space, no? It is not that. For some confusion, for some reason, this is called operator weak topology, okay? T lambda converges to T if T lambda xi eta converges to T xi eta. This is the weak topology. Okay. Strong topology is just, I mean, strong topology, strong convergence will imply this convergence. Okay. This is the weak convergence. I mean, the point-wise convergence is the strong convergence. Here, the point-wise convergence happens in weak topology. That's what this says, right? This is the weak topology. I mean, if you just have some xi n, some xi lambda eta converges to xi eta, means xi lambda converges to xi in weak topology of the Hilbert space. Point-wise convergence happens in the weak topology is what is called operator weak topology. Okay. Point-wise convergence is strong convergence. Point-wise convergence in the weak topology is operator weak topology. Okay. So this happens in the weak topology. That's what this means. So this just means f of t xi eta, okay, equal to integral over c f of lambda. You have that du mu xi eta, no, that complex measure. You integrate with respect to lambda. This is what this means. This is, I mean, you can take this as the meaning of this. Okay, this is equal to this means f of t is determined by this. Okay, so f of t xi eta is, this is just a complex, I mean, integration with respect to complex measure. If you don't like it, that complex measure can be written as sum of 4 positive measures. So you just integrate with respect to those positive measures. Okay. So this is the meaning. Are you defining? Complex measure. Then the f of t xi eta is this. That's what I'm saying. No. Mu xi eta comes through the. I'm saying direct is a unique spectral measure. Given a t, there is a unique spectral measure. That spectral measure satisfies this condition. That's all. Yeah. Okay. And finally, the support of this p, whatever that spectral measure p is sigma t. That is, support can be defined in 2 ways. This is for all u open and u intersection sigma t is non-empty. Okay, then p of that u is not equal to 0. This is equivalent to saying the sigma t, this is and there is something else, and p of e equals 0 if e is contained in sigma t complement. Okay. I mean, the measure is concentrated in sigma t, and that is the smallest closed set such that p of sigma t is 1. Okay. Sigma t is the smallest closed set, say smallest closed set f, such that p of f equal to 1. 1 is the measure of the whole set, I mean C, right? So this is how you define the support, or you can take this as a definition. It will follow that is the smallest closed set with p of sigma t equal to 1. Okay. Uniquely defined with respect to this property. Yeah, this is the property which defines the spectral measure. Spectral, yeah, uniquely defined. These are all properties. If you have any spectral measure, this will follow. This is the property. So property 3 is the one which it determines, and this is also a property. Yeah. No, definition of spectral measure is that. So given a t, there exists a spectral measure which satisfies this condition. All 4 conditions I have said. Okay, these are all follows from that being a spectral measure, it will follow. And this condition, it determines the t. Exactly. This is the uniqueness. I mean, it is this condition which determines the P uniquely. Yeah. Given a spectral measure, you can do this integration and you get a operator. And given a T normal, you get a spectral measure so that when you integrate, you get the operator back. That's all. From the spectrum and spectral measure, you get the operator. You get all the information about it. Okay. Okay. Let's prove it. It's all quite simple. I will take 5 more minutes. So the other statements are clear, I believe, because if n equal to 1 to infinity En equals E, okay, then we know that these functions, I mean, summation 1 En equal to 1E, right? This converges in almost everywhere or whatever. So we know that the projections, the spectral projection converges. This is just a, oh, I didn't say how to define P. Sorry. Then only it all follows. Sorry. So proof. To define P of E, just a spectral projection. 1E of T. We have the functional calculus. You define P of T to be 1ET. Okay. Then clearly it's a spectral measure, right? Maybe not. Maybe, I mean, P of T 180, or if you want, you take the intersection with sigma T. We have defined it for any by taking the intersection with sigma T. So, okay, take this as a spectral measure. We have the measurable functional calculus. Using that, we define P of E equal to 1E intersection sigma T. Okay. Then clearly we know that if, I mean, E, then we know that this sum up to from capital N will increase to E. So that will increase to that, and it's clearly additive and all that is clear, I believe. You have already seen that, right? Okay. Then this one increases to 1. Okay. Then this P of this increases, converges strongly to P of this. Okay. And you can take the sum outside and it's clear. So it's clearly countably additive. Okay. And the convergence is a strong convergence. Okay. And strong convergence, the convergence. So those things are clear. So one is clear, and the second one just follows from the continuity, right? The second one, this follows from the continuity of the inner product. That's all. Same thing. You have a summation and you can take it out and, right? Continuity of the inner product. Third one, see, you have to prove that this is a complex measure. The complex measure, the thing is, it has to take values in complex. I mean, third one also follows from the continuity of the inner product. And it also actually, if you want to consider the integration of the thing, the polarization identity says that any, I mean, it says that you can write that as this is the polarization identity, no? Xi eta equal to summation 1 by 4 I power k. Okay. So mu of xi eta equal to 1 by 4 summation I power k mu of, I mean, I power k, this is only for the k equal to 1 to 3, k equal to 0 to 3. For 1 and 3 only, this is I minus I. Okay. I mean, this can be written as sum of 4 linear combination of 4 positive measures. Okay. Mu xi plus I power k eta. Okay. So this is the complex measure. Okay. All that will follow. And we have to prove only the integration part, right? Integration part and the support statement. Okay. So we know this satisfies f of t xi eta equal to integration f of t d mu xi eta is satisfied if f is simple. Okay. You take a simple function 1 xi eta, so it is precisely that. If you integrate with respect to that mu, it is precisely the same thing, same statement, right? You take f equal to summation lambda I 1 vi. Okay, then this LHS is equal to summation lambda I f of 1 ei. 1 ei is just p of ei, right? 1 ei is the p of ei xi eta. That is how it is defined. So this is equal to summation lambda I mu xi eta of ei, which is exactly the integral, right? F of lambda d mu xi eta. This is the integral. For simple function, this is how it is defined. So it is satisfied for simple function. We have to prove it for general function. So we just approximate. Forget about this. This f is not any f. This f has to be bounded. I mean, we can prove it for L infinity. We take it for bounded. Okay, f is bounded, measurable. Okay. Okay. Now, if f is bounded measurable, if you remember your measure theory class, any bounded measurable function can be uniformly approximated by simple functions. Okay, so there exists a p simple such that p f minus p, this infinity norm, the L infinity, I mean, it's point-wise infinity. We take the supremum, okay, this is less than epsilon. Okay. These are all bounded functions, so you can talk about infinity norm. So infinity norm is less than epsilon. Okay. Now, if you take this, you want to prove that f of t xi eta minus integral f d mu xi eta. Okay. You want to talk about this mod. This is less than or equal to f of t minus p of t xi of t minus z of t xi eta using triangle inequality plus p of t xi eta yeah, p of t minus xi eta minus this is okay, integral p of t p d mu xi eta. Okay. Then this is integral p minus f minus p, okay, d mu xi eta. Okay. Now this, of course, less than epsilon. We can make this less than epsilon. This is uniformly f minus, I mean, f of t minus p of t. I mean, this is isometric, no? So this you can make it less than epsilon times norm xi times norm eta. The norm of f of t minus phi of t is less than epsilon. You can make it. F minus phi is less than epsilon. The supremum norm is less than epsilon. Okay, the functional calculus is isometric. So you can make this f of t minus phi of t. This is less than epsilon. The norm of this is less than epsilon. So this is less than epsilon times norm xi plus norm xi norm eta. And this is, of course, you can make it less than epsilon. Okay, and you can make this. You can take, of course, the mod inside. And f minus p is less than this. So this is epsilon times the whole set. I mean, the complex measure of the whole set, which is equal to integral, I mean, mod of this, whatever. which you want is again norm z times norm beta, okay, less than or equal to. Okay. So this minus this is epsilon times some bounded constants. So this should be 0. So this should be equal to, they are equal. That's all. So uniqueness will follow because if you take, are you getting tired? It's okay, no? So this is just uniqueness. So if there exists P1, P prime, P prime, two spectral measures, okay? Okay. Then such that that condition is satisfied, this condition, f of t is a eta equal to this. So in particular, we will get f of lambda dp equal to f of lambda dp prime for all f, for f bounded. And of course, this is true for any polynomials. This will in particular have z, I mean, this will be true for polynomials in z and z bar, right? This is true for all. What do we have to prove? We have to prove that P is equal to that. Okay. That determines yeah. Suppose there exists two spectral measures. No. What is that statement? Statement, there is no statement, no? That just says that the functional calculus is, this is just the functional calculus, right? So the statement is just with lambda, I think. There exists a unique spectral measure with lambda there, I think. Then if it is true for lambda, then it is true for lambda power m, lambda power n, true for polynomials, so it is true for all f. So they have to be equal. I mean, that just says that see, this will imply that if suppose if this is true, okay, this is true for all bounded functions. So in particular for any one e, there is really nothing in the statement, right? P of e equal to that. So the statement here should be there exists a unique function such that this happens. There exists a unique spectral measure such that if you integrate the function f of lambda equal to lambda, that f naught function, then you get t. You get the t back. So if you get with respect to some spectral measure, then it is true that, I mean, this is this spectral measure. If you write like this, integral f1 dp, integral f2 dp is actually integral f1 f2 dp. This is true for all simple functions, and so from that it will follow that if you take any zm, z power m, z power z bar power n or something, so those two will be same. Then by Stone-Weierstrass theorem, we will get that functional calculus is same with respect to this p. If you have a spectral measure, you get a functional calculus using this f. I mean using this integration. Okay, the functional calculus is same for both the operators. That's both the spectral measure. It says, and it has to be same when you extend to L infinity. The spectral measure has to be same. Okay, that's all it says. Because it will coincide on all indicator function. Okay, so I will prove the support statement. That's the only statement left. So if U intersection sigma t, let's prove the other way. So suppose P of U equals 0, U open, Okay, then we prove that the intersection with the sigma t is empty. Okay. And Z is in U, then there exists a open ball D is a R contained in U. Okay. Okay. And of course, P of that open ball is also 0 because that is a subset equal to 0. Right? Okay. In particular, this function 1 by, I mean, you call it Z naught for the time being. I mean, Z naught is arbitrary, but call it Z naught. This function is well defined, right? Because this has, I mean, well defined with respect to as I mean, in L infinity of what is that mu? There's some confusion about mu, no? I'll make it clear next time. Okay, I'm getting lost. See, this L infinity can be defined through P also, but I mean, to make it rigorous, we have to define it through mu, this L infinity. Okay, this function will be I mean, because it's, I mean, this has measure 0, all those mu measure will be 0. Okay, so this will be an invertible in that L infinity. So that will prove that Z naught is not in the spectrum for arbitrary Z naught. So that will imply that this Z naught is not in the spectrum. Okay, so U intersection that sigma t is empty. So we have proved the other statement. If P of U equal to 0, then U does not intersect with the spectrum. The statement here is U intersects with the spectrum, then P of U is not equal to 0. This is proved. Okay. So we will discuss it again with the other problem.